Hey everyone, this is Professor Rogers. Welcome to my video on how to run a binary logistic regression in Microsoft Excel using the XLMiner tool pack. Most of you have been exposed to binary logistic regressions, but didn't know it. When you are in the car listening to the radio or scrolling through news stories, you might hear or see a headline such as, "The likelihood of getting cancer goes down 15% if you eat dark chocolate every day." A statistic like that normally comes from a binary logistic regression. Binary logistic regression is used when we have dichotomous variables. Now, by dichotomous variables, we mean there are only two outcomes. So we're measuring a success or failure. Somebody might be arrested or not arrested. You might have passed a test or not have passed a test. You could have answered some questions and you said yes or no to a question. So that's what we mean by the dichotomous outcomes, that we have two of them and they're usually measured as 0 or 1. You'll notice that I have binary in parentheses. There are different kinds of logistic regressions. We can have a logistic regression for ordinal data. We can have a logistic regression for nominal data when there are 3 or more categories. But those techniques are not that common. Binary logistic regression is very commonly used, so much so that people might convert their data into a binary format if it's not in a binary format. And so as a result, a lot of times we simply say logistic regression, and it's implied that it's in binary. That, by the way, for those of you using XLMiner, is what happens there. In XLMiner, it is not called binary logistic regression, it's called just logistic regression. However, those of you who go on to something more complex and might be using SPSS, you will see it will specify the different types of logistic regressions in the software menu. Although we are using the term regression, the logistic regression is fundamentally different from the ordinary least squares regression that you would have had in earlier in this class, or if you're in someone else's class, usually we're in a sequence, and logistic regression comes towards the end of the sequence in a semester. And the basic difference there is that we are no longer trying to fit a line, we're trying to fit a curve. And that creates an entirely different type of formula. And instead of focusing on the slope or some multi-dimensional equivalent of a slope, if we have multiple independent variables, we are now focused on something called the odds ratio. We can have any level of measurement in our independent variables. This model usually works best with categorical variables. So we'll have, when we have the categorical variables, we have to break them down into a variable block, just like we do with ANCOVA models and OLS regression. So there's always implicitly, if not stated directly, a reference category with that block, or even if we're using a single binary variable, not having that result becomes the reference category. But we can use interval ratio data. We will, as part of this presentation, look at a couple common problems with ordinary least square. Sorry, a couple common problems with logistic regression, and that's overspecification of the model when we have too many independent variables. And we'll also look what happens with the use of interval ratio variables. We have the possibility that we could end up with coefficients that are too small to be useful. What we are trying to fit in logistic regression is the logistic curve, also referred to as the S-shaped curve or a sigmoid. In the example here, we are trying to use the hours spent studying to predict the outcome of an exam. You can pass the exam or fail. And here is the scatter plot of that relationship. On the bottom, the axis is the hours spent studying, and the axis on the left, you'll notice on the top it says 1, and on the bottom it says 0. So 1 is you passed the exam, 0 is you failed. You'll notice here on the bottom, towards the left, there are a bunch of dots in a line. Those are the people that failed the exam. On the top with the 1, you also see a bunch of dots. These are more towards the right of the graph. These are the people who passed the exam. You'll notice there are no dots in the middle. So when we have two interval ratio variables and we do a scatter plot, usually we see a cloud in the middle. We don't see any cloud of points there. That's because there aren't any. There are only two possible values, so you can't form the cloud with that. We do on the left axis have numbers listed between 0 and 1, and those are the probabilities of occurrence. Now, when I was a graduate student, which is now ancient history because we're talking the 1980s, if you had this problem and wanted to run statistics, you might use an ordinary least squares regression for that because we didn't have logistic regression. We might have had it in theory, but logistic regression was memory intensive for the computers of that era. So if you ran one, you pretty much, if you were running on a mainframe and you were running a logistic regression, if there was any size to that data set, you could easily stall the computer, bring it down, use all the memory on the mainframe computer. But if you did an ordinary least squares regression, what that would actually predict, the outcome in the model, the predicted value, would be the probability of the occurrence of passing the exam given the characteristics of the independent variable. The problem with that model is that the ordinary least squares regression can predict a value higher than 1 or less than 0, which in this case is completely nonsensical. It's predicting things that cannot happen. So logistic regression takes care of that problem by trying to fit this S-shaped curve that we have here. So there will be probabilities, but they're going to be probabilities along this curve. What I've just added to this slide is the equation for fitting the curve. And you'll notice major differences from the equation of a line, but that the equation of the line is still kind of embedded in here. So let's go to the denominator and we see that italicized E. That stands for a natural log. I'm not going to go through lots of discussions about logarithms here. That's something that you would have had in math class, but it's important to note that that's what contributes to the curved shape of our model. And you'll notice that the natural log has an exponent that's quite long. And inside the parentheses of that exponent, we see beta naught plus beta 1 times x. Those symbols you should recognize from the general linear model. But, look at where it is. It's an exponent to a log in the denominator. So it's no longer functioning as a slope. It is something different. And so that's what we really will be looking at here. We're going to show you how to run this logistic regression in Excel. And we're also going to interpret this, show you how to interpret that. And that's where we look at this new stat called the odds ratio. Our example will come from the states data set. So for the benefit of those of you who are not in my undergraduate stats class, we have a data set of 50 states that we use to try out various statistical techniques on. So I'm showing everyone here the variables that I'm using for this problem and for a few others related to this within this video. So first off, we have whether or not the state, whether the inhabitants of a state as collectively reach a high level of education. Now that's kind of the technical way to describe that, but educate high means you have, relative to other states, lots of well-educated people. That's what that means. There are 9 states in the United States that got that designation. Then we see the variable block for the variable region. So we have Northeast, Midwest, West, and South broken out as dummy variables. And so this is something that you would have done in an ANCOVA model if you were running it in Excel. Finally, we have the population from the year 2018, which we will look at later in this video. Within some of the newer versions of Excel, we do have the XLMiner tool pack. So it's not in the traditional desktop application, but it is in some newer ones. Students in my classes, you've already been encouraged to use XLMiner, so hopefully you will be able to find it. But if you haven't already, you can find it in Office 365, in your campus Office 365 in the upper left-hand corner in the icon. That version of Excel should be giving you the XLMiner tool pack. If you look at the menu that appears, and you should know by now how to find that menu, you'll notice that if you scroll down just before linear regression, I'm sorry, just after linear regression, you will find the logistic regression function. And so you see it highlighted here in a slightly different color. That's not the end of the menu. It's just that on my computer, the whole menu does not fill the screen at that moment. So I have to scroll down further to see the things below that. So don't be confused by that. That's just why I mentioned that. Well, if we click on the logistic regression function, this is the dialog menu that we get. I have this set up for a particular problem. So I'm going to look at whether states in the Northeast have higher levels of education in their population than the rest of the country. So my Y variable here is the range for the binary variable that indicates whether or not education is high in a state. The X range is my variable for the Northeast. It's 0, 1. 1 if you're in the Northeast, 0 if you're in the rest of the country. I have labels checked. As you know from my classes, I'm a big advocate of putting labels on your columns. When you're doing a problem right at that moment, it's not a big deal. But when you come back a week later, it's hard to remember what you did. And so the labels help you. Confidence interval by default is set at 95%. And I'm going to put the output in cell FAF1 of my spreadsheet. So we're going to then click OK. Here are the results we get. You'll notice they sort of look like how regression results come out. Not exactly. I did format this. As those of you who are my classes know, I'm big on formatting output so that you can read it better and interpret it better. Because for these numbers that are decimals, we end up with some very, very long numbers, and most of the decimal points, most of the things to the right of the decimal point are not needed. So I did round all of the decimated numbers to having only 2 decimal points. So it's a little neater than you would get in the output. Now we're going to blow up a couple pieces of this in order to understand what's going on here. And this is from the bottom, that long piece on the bottom, which is what gives us the coefficients for fitting the curve. So we had that weird equation that I showed in the bottom of the graph a few slides back. These are the numbers that go into that. The intercept is beta naught, and then the coefficient for Northeast is beta 1. Northeast is a binary variable, so our reference category would be states that are not in the Northeast. And what we have there in that first column, coefficients, is the beta naught column. And that is the so-called regression coefficient that we all know and love. Again, it's not a slope anymore, but it's the closest thing that we have to that slope in the logistic model. Then we have our measures for statistical significance, the standard error and the p-value. Those are built on the coefficient. So the idea here is that 1.75 for Northeast, if we build a confidence interval around that coefficient, that 0 will not be in that confidence interval, meaning that our result is statistically significant. That's the same interpretation we've had all the way through, so no big change there. The odds ratio is the things that's different, because as we have already highlighted, that 1.75, it's hard to say what that means. We're usually not interested in the odds ratio of the intercept, as some packages will not even give you one for that. We are interested in this 5.76. Now we're going to interpret the odds ratios. So the null hypothesis of an odds ratio is a value of 1. So again, think about what we have done as we've moved into the bivariate statistics and into OLS regression. Usually the null hypothesis in those stats is that our coefficient is 0. And when the p-values are calculated with logistic regression, they are calculated off that coefficient value in the first column. So again, that we're saying 0 when something is statistically significant, as is the case in this model with Northeast, we are saying that the results are going to be statistically significant based on the 0. The equivalent to 0, however, in odds ratio terms is 1. So an odds ratio of 1 corresponds with a coefficient of 0. The way you can think about that 1 in terms of odds is betting on horses. A 1-to-1 odds in horse betting are uninteresting odds. You give $1 and you get $1 back, and it's guaranteed. God, it's just, why would you do it, right? It's boring. Now 5.76 is not boring. So 5.76 is greater than 1. So what we're saying is the likelihood of a state having a highly educated population increases with the state being in the Northeast. And a Northeastern state is 5.7 times more likely to have be classified as a high education state when compared to states outside of the Northeast. Now we can take that times, and we can also express it as a percent. It's 476% times higher. What we have to do is we have to factor in that the percentage increase, we have to take out that 100%. So like with if something is twice, 2 times higher, that's not a 200% increase. That's a 100% increase. It's double. So that rule applies as we go up. So when it's 5.76 times higher, it's not 576% higher. It's 476% higher. So I showed you the calculation here, how to get that. When you do it, it doesn't really give you the percent calculation. You have to interpret it that way. So it would be the odds ratio minus 1, and then take that quantity and multiply it by 100. And it is very common when you're less than 100% to use the percent number when talking about an increase. Now, what happens if the odds ratio is less than 1? So I've got a hypothetical one here. Let's say we got an odds ratio of 0.85. We could say that's 0.85 times lower than the reference category. That's a little strange way to talk about it. We could also say it's 15% lower. And how did we get the 15%? I subtracted the odds ratio from 1 and then multiplied that by 100. So I flipped the odds ratio and the 1 around. Now I don't have to do that. I could use the formula above, and then I would just get a minus 15 uh, for my percent rather than a plus 15%. I just would have to know that I did that. So it's not a big deal. If it really freaks you out that I changed the equation below, you can still use the one above and end up at the right place. On the top of our output were the regression statistics, and I've reproduced them here. The only one that might really matter is the chi-square statistic. And this is the chi-square that we're used to that can be used in many ways besides what we did with crosstabs. The chi-square in this case is 4.37. The degree of freedom would be 1 because we have one variable in our model. Now, we could use this to interpret the size, the goodness of fit of the model. There are different camps there. So you'll find I don't really spend a lot of time with this, especially in undergraduate classes. There's some people who will come out and just say, you know what, we don't have an R squared. Everything else is kind of convoluted. Let's just not talk about the goodness of fit of logistic models. I like to do that, at least even if this is not precise in the way that an R square is precise. It gives me an idea of the size of the fit or the model. So we could interpret the chi-square with 1 degree of freedom the way we might if we saw a chi-square in a contingency table. Jumping down to the iterations number, that number is tied to the issue of fitting a curve. So fitting a curve is something that's difficult for a computer to do. So unlike the line, where the computer will pass through the data once, it is necessary to look at multiple attempts to fit the curve. And the idea is that each time I attempt to fit the curve, I get closer and closer and closer. And at some point, the computer says, I'm close enough. That's a good enough estimate. Any improvement in my model will be tiny. So what this is saying is that it ran the model 5 times to get the outcome. If you were to run this on your computer, you might get a slight delay that you didn't see when you run some other statistics. And that's because it's actually doing this multiple times. On this page, we have an example of overspecification. And what I used is the full variable block for region as my predictor. So Northeast, Midwest, and West are the portions of the variable block that I used, and then South becomes my reference category. What I want to draw attention to is the odds ratio, and look at that ridiculously large number. Now, a common mistake of people who are new at stats, the first time you see that number is, wow, what an incredible relationship I found. The answer is you did not find that relationship. That is an artifact of having too many things in the model specified. There just are not enough states in the combination of region and educational level to run this model, and that gives you very distorted results. And so we call that overspecification. Now, in this example, I used population to predict the level of education of a state. So the hypothesis would be as a state becomes more populated, the educational level of the state should go up. You know, have more resources, more people, so you could have more educated people. That's kind of the idea there. And look at what happens in this case with population. The coefficient is 0, and the odds ratio came out as 1. This is an artifact of the units that it's measured in. So we're trying to measure a qualitative change in educational quality with a coefficient that gives me the change for one person. Now, many states have millions of people in them. So the change from one person would be so tiny that it's hard to measure. Mathematically, you can do this. Mathematically, you can put an interval ratio variable into a model like this and it will work, but not all the time. So you might do something to correct it. You might create categories or you might rescale the units somehow. Now, I did something like that here with this second part of this example. So below, I have a slightly different model for population. And what I did was I divided by population by 1,000,000 people. So it's still an interval ratio variable, but now my coefficients make a little more sense when I look at them. So that's something that you might be aware of. Again, you can run an interval ratio variable as an independent variable in a logistic model. It just doesn't always work well, just because of the nature of that variable. Here at the end, I just want to go through everything we looked at. Logistic regression is the technique when we have a dichotomous dependent variable. So that would be a 0-1 outcome. It's different from ordinary least squares regression because now we are fitting a curve, not a line, and we are basing the interpretation on what we call an odds ratio. We can use any level of measurement for independent variables, and if we are using categorical variables, we need to deal with the variable block. Now, I mentioned here 3 or more categories. It's kind of implicit if you have a single binary variable what the reference category is, but we want to highlight in 3 or more categories, you have to use that technique where you drop one. We looked at a couple common problems with logistic regression, one being the overspecification of the model, and the other being how interval ratio variables might be hard to interpret because they yield small coefficients. That's it for today, and I hope you will have a good time ahead.